Theovis, the idea made visual. You first met the dot product as a rule. Multiply matching components, add them up. A recipe with no obvious meaning.
Right. A1, B1 plus A2, B2. I could compute it, but I never knew what the number was telling me.
By the end of this, you'll see that one number quietly powers projection, the cosine of an angle, and even matrix multiplication. They're all the same idea. Here's the definition you know. Pair up the components, multiply, and sum. Clean and mechanical.
But why that combination? Why should adding up those products mean anything geometric?
It took decades to settle this. Grassmann and Hamilton wrestled with how to multiply directed quantities, and only later did Gibbs and Heaviside distill the clean dot product we use today.
So the tidy little formula I take for granted was actually the survivor of a long fight over how vectors should multiply.
Picture two vectors. The dot product takes them and returns a single number. The question is, what does that number measure?
Let me guess. Something about how much they point the same way?
Exactly the right instinct. Watch. Shine a light straight down onto the direction of A. The shadow that B casts along A, that length, scaled by how long A is exactly the dot product.
Oh, so the dot product is literally measuring how much of B lies along A. It's shadow.
And when B swings more in line with A, the shadow grows. Swing it away, and the shadow shrinks. If we want the shadow as an actual vector, here it is. The dot product of A and B divided by A's own length squared times A. The dot product sets the length. A sets the direction.
So projection is built entirely out of dot products. Two of them, really. One for B onto A, one to normalize A.
Written out, that shadow is this. The two lengths multiplied times the cosine of the angle between them.
So the same number we got by multiplying components also equals lengths times cosine? Those look nothing alike.
And yet, they're always equal. That coincidence is the whole secret. Hold on to it. Let's make it concrete. Take A equals 3, 4, and B equals 2, 1. The dot product is 3 times 2 plus 4 times 1, 6 plus 4, which is 10.
And the lengths. A is 5, B is about 2.24. So cosine theta is 10 over their product, about 0.89. An angle of roughly 27 degrees.
Real vectors, a real number, a real angle. The whole machine on one slide. Because of that cosine, the sign carries meaning. Point B alongside A, and the dot product is positive. Square them off at 90 degrees, and it's exactly 0.
And if B points the opposite way, the cosine goes negative, so the dot product is negative too.
So one number tells you same direction, perpendicular, or opposed. Because cosine never exceeds 1, the dot product can never beat the product of the lengths. That's the Cauchy-Schwarz inequality. quietly one of the most used facts in mathematics.
So it's saturated only when the vectors are perfectly aligned. The geometry puts a hard ceiling on the algebra.
So forget the recipe for a moment. The dot product is a meter of agreement. Big and positive when two vectors align, 0 when they're independent, negative when they fight.
That's such a cleaner way to hold it in my head than multiply and add.
One special case does enormous work. If the dot product is 0, the vectors are perpendicular. That single test is how we check right angles in any number of dimensions.
No protractor needed. Just compute one number and see if it's 0.
That 0 test lets you manufacture clean coordinate systems. Take any messy vectors and repeatedly subtract off the shadows along the ones you've kept, Graham-Schmidt, and you're left with a perfectly perpendicular set.
So every step is remove the part that overlaps, measured by a dot product, orthogonal axes, built by subtraction.
Why do the component recipe and the lengths times cosine agree? Expand the squared distance between the vectors, and out falls the law of cosines.
So the algebra and the geometry are forced to match? It's just the law of cosines wearing a different outfit.
And none of this is stuck in 2 dimensions. In 3 or 300, the dot product still casts B's shadow along A. Here it is in 3D, the projection tracking B as it swings.
So how much of one vector lies along another makes sense no matter how many dimensions we're in. That's powerful.
Here's a quiet realization. A vector's coordinates aren't fundamental. Each one is just the dot product of the vector with an axis direction. Coordinates are shadows on the axes.
So even writing a vector as a list of numbers is secretly doing dot products. It really is hiding underneath everything.
Once you see it as a shadow, it's everywhere. In physics, the work done is force dotted with displacement. Only the part of the force along the motion does any work.
So pushing a crate sideways does nothing useful? Only the shadow of your force along the path counts. That's a dot product deciding it.
Push at an angle, and only the cosine part counts. Push perpendicular to the motion, carrying a bag down a level hallway, and you do, formally, 0 work.
Which finally explains why physics says holding a heavy box still is no work, even though my arms strongly disagree.
Now, the surprise. A matrix takes the whole grid of space and bends it, sending the basis arrows to new places. That's what matrix multiplication does to a vector.
Okay, the grid is shearing and stretching, but what does that have to do with dot products?
Look at how you actually compute a matrix product. Every single entry is a row of one matrix dotted with a column of the other.
Wait, so a matrix multiplication is just a whole grid of dot products run all at once?
Exactly. Projection, the cosine, and matrix multiplication are 3 views of the same operation.
Let me line it up. The dot product is a shadow. That shadow equals lengths times cosine. and stacking many of them is matrix multiplication.
All one idea, which is why this little sum of products quietly runs almost everything that follows. Here's a heavyweight application. When data won't fit a line exactly, least squares finds the closest fit by projecting the data onto what the model can reach, and every piece of that formula is dot products.
So, curve fitting, regressions, the trend lines everywhere in science, they're all just projection. The dot product casting a shadow onto the best we can do.
This is why search engines and recommendation systems compare things with cosine similarity, the dot product of normalized vectors.
And a single neuron in a network is basically a dot product of inputs and weights, then a little bend. The dot product really is everywhere.
Least squares fitting, Fourier analysis, projections onto subspaces, all the same shadow, taken over and over. One more that surprises people. Take two datasets, center them, and the correlation coefficient between them is exactly the cosine of the angle between their vectors.
So, these two things are correlated literally means their vectors point in similar directions. Correlation is a dot product in disguise.
Push it one step further. If vectors can be dotted, so can functions. Multiply two functions, integrate, and you get their overlap. That inner product is exactly how Fourier measures a frequency.
So last time's winding machine was secretly dotting the signal against each rotating vector. It all connects.
Mathematicians distilled what a dot product must do. It's linear, it's symmetric, and a thing dotted with itself is never negative. Anything obeying those rules is called an inner product.
So, inner product is just the grown-up name for any honest agreement meter. On arrows, on functions, on whatever space you like. So the whole thing is one sentence. The dot product measures how much two vectors agree, as a shadow, as a cosine, and a matrix is just many of them at once.
That's it. A single sum of products, carrying the geometry of angle and projection into any dimension you like. If you want the rigorous version of all this, these texts build the inner product from the ground up. We've now seen vectors agree through the dot product. Next, we ask what happens when one number per direction isn't enough, and meet the tensor.
From shadows to tensors. See you there?
If it finally clicked, subscribe. It really helps. And I'll see you in the next one.